Alright, so in this video I'm going to go through the January 2012 Unit 2 paper, so looking at mechanics, materials and waves. So let's start off with some mechanics. So we've got a ship and we're trying to use a sail as a way of reducing running costs to provide some of the force or energy if you like. So we've got a sail and it's at 40 degrees to the horizontal. So the average tension in the cable is 170 kilonewtons. Show that when the ship travels 1 kilometer, the work done by the sail is 1.3 times 10 to the 8. So the key thing here is work done is force times displacement in the direction of that force. So what we're going to be using is the equation W equals F S cosine theta. So the force is 170,000 because it's in kilonewtons. The displacement is 1,000 and the angle between them is 40 degrees. So if we put all that in, we end up with 1.302 yada 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 times 10 to the power of 8 joules, which is roughly 1.3 times 10 to the 8 joules there. So that's worked out just fine. Okay, so with the sail and the engines operating, the ship is traveling at a steady speed of 7 meters per second. Calculate the power developed by the sail. So what we can do is we're going to be using the equation P equals F V cosine theta, because we need the force in the direction of the velocity. So the force was this one, the speed was this, and again the angle between the force and the motion is cosine 40. So let's do that calculation. We end up with 9.1159 times 10 to the power of 5, which are two significant figures which would be appropriate here would be 9.1 times 10 to the 5 watts there. Okay, so that gives us the power. So let's move on to the next question. Calculate the percentage of the ship's power requirement that's provided by the wind when the ship is traveling at this speed. So the power output of the engine is 2.1 megawatts. So the percentage is going to be the power, the sail, as a fraction of the total power times by 100%. So we just calculated, so let's get everything in megawatts. So we've got 0.911 divided by 2.1 plus 0.91, that's the total power put in, times by 100%. And then once we do that, we get a figure, when we round it to two significant figures, of 30%, as that one there. The mistake a lot of people make is they just put 2.1 on the bottom line. Remember, we have to put percentage of the total power, not just the power from the engines. Okay, so the angle of the cable to the horizontal is one of the factors that affects the horizontal force exerted by the sail, the ship. So two other factors that would affect this force. So if you want to increase a force from a sail, you can make your sail bigger or increase its area, so then there's more area for air particles to collide with. And also you can increase the speed of the wind, because then it'll have a greater change in momentum when it strikes the sail, so you get a bigger force. So those are the two I would go for. So area of the sail would be 1, and then speed of the wind would be a second one that's appropriate there. Okay, so that finishes that question. Let's move on. So continuing with mechanics, we've got an electronic bike or an e-bike, and then we've got a rider with mass of 83 kilograms. Sorry, the bike and rider have a total mass of 83, and they're going up a hill. And we know the hypotenuse and we know the height change. So the cyclist begins at rest at A and accelerates uniformly to a speed of 6.7 at B. The distance between A and B is 50 meters. Calculate the time taken to travel this distance. So I'm going to go with some suvat here. So let's write out what we've got. So I'm going to use up parallel to the slope as the positive direction. So the displacement is going to be 50. The initial speed is 0. Final speed is what we're looking for. We don't know what the acceleration is. Sorry, we do know what the final velocity is, what we're talking about. We don't know the acceleration, and we're trying to find out what the time is. So that's the general form of suvat that we are looking for. So that's the properties. So we want the equation that doesn't have A in it. So that's this one right here. So S equals U plus V over 2 times by T. U is 0, so let's get rid of that straight away. So T is 2 times the displacement divided by the final velocity. So that's 100 over 6.7, which will be, I think, like 15, or it looks like 14.925, blah, blah, blah. So that's 15 seconds to 2 sig figs there. Okay, so calculate the kinetic energy of the electronic bike and rider when at B, giving our answer to appropriate number of significant figures. So kinetic energy, it's in your formula sheet, but you should know this by now, half m speed squared. So it's half times the mass, which was 83, times by 6.7 squared, which comes out as a value of like 11862 blah blah blah. So that's going to be rounded to 2 sig figs. So that's 1.9 times 10 to the 3 joules to 2 significant figures, which we can see here. That's the kinetic energy. The next one wants us to calculate the gravitational potential energy gained between A and B. So it goes up by a height of 3 meters. So change in GP is calculated by doing mg delta h, which is 83 times by 9.81 times by the change in height, which is 3, and when we put that in, we end up with 2443. So that's going to be 2.4 times 10 to the 3 to 2 significant figures. Between A and B, the work done by the electric motor is 3,700, and the work done by the cyclist pedaling is 5,300. Calculate the wasted energy. Useful is going to be the increase in kinetic energy plus the increase in GP. Which we've got. So that was, so the kinetic energy we had was 1900 or so. The GP we had was 2400. So hang on, that was, kinetic energy was 1862 blah 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 plus 2443, which is a value of 4305.9. The input energy is those two values we've got in the question added together, which is, what's that, 9,000 there. And then, so all we need to do is find the difference between that. So waste equals 9,000 minus 4305.9. blah, blah, blah. Let's do that. Which is 4695, so I'm going to write that as 4.7 times 10 to the 3 joules there as 2 sig figs. Okay, so state 2 causes of this wasted energy. So some of it will be doing work done against air resistance, and then we'll also have some work done against friction, both of which will essentially transfer useful energy into thermal energy. So let's put those down. So we're going to have work done against air resistance would be one of them, and then another one was going to be doing some work done against friction. And we can be specific about where that is. At contact with ground and in moving parts of the wire. So we can be a bit more specific, so we really should be there, otherwise we're not really earning those 2 marks there. So those are the 2 sources of wasted energy. Alright, so let's move on to question 3. Right, so we've got an aircraft designed to take off and land vertically, so pretty much like a regular fighter jet by the looks of it, and it can also hover without moving horizontally. To do this, we get upward lift by directing a jet engine straight downwards, and we've also got a fan near the front we can use to do that too. So the weight of the aircraft is 180 kilonewtons, and the distance between the fan and the centre mass is 4.6. The distance between the jet engine and the centre mass is 2.8. So this is looking like a moments question because we've got forces at different distances. So calculate the moment caused by the weight of the aircraft about point X. So we've got essentially moment is the force multiplied by the perpendicular distance between the line of action of the force and where we're taking moments about. So the force is 180,000. The distance we can see is 2.8, and then if we put that in, we can get a value for this, and when I do this I get a value of 500,000, or it's actually 504,000, so it's going to be 5.0 times 10 to the 5 Newton meters to give it the 2 sig figs there. Okay. So moving on to the next question. By taking moments about X, calculate the lift fan thrust if the aircraft is to remain horizontal when hovering. So if it's going to remain horizontal, that's not going to be rotating, so the moments must be in equilibrium. So what I'm going to do here is apply, so the moment of the weight force must be equal to the moment of the fan. So if we go up, the fan is a distance of 4.6 plus 2.8, so that's 5.4, 7.4. So that means the force from the fan must equal the moment of the weight force divided by the distance of the fan from X. So we've got this, it was like 504,000. Distance of that is 7.4. So when we calculate that answer, we end up with 68,000 newtons, so 6.8 times 10 to the 4 newtons is the force there. Okay, so that finishes part 2. Let's calculate. So now I want us to calculate what the engine thrust is. So I'm going to apply linear equilibrium, so the upward force must equal the downwards force. So essentially what we've got is the forces upwards. We just calculated, we've got 68,000 plus whatever the force is must be equal to the total weight force of the aircraft, which is 180,000. So when we calculate that, that gives us a force of 112,000. That's 1.1 times 10 to the 5. Two significant figures there. Okay, so that's your engine thrust. So having taken off vertically, the jet engine outlet is turned so that the engine thrust acts horizontally, and the aircraft accelerates horizontally to a maximum velocity. The forward thrust produced by the jet is 155 kilonewtons, and we've still got a weight of the aircraft of 180 kilonewtons. When the resultant horizontal force is 155 kilonewtons, calculate the acceleration. So first, we need to work out what the mass is, because we've got the weight force. So if we divide the weight force by g, that will tell us what the actual mass is, because we're going to need that for Newton's second law. So that's like 18349 blah blah blah. Acceleration is resultant force divided by mass. So that's 155,000 divided by 18349 blah blah blah. And when we do that, we end up with an acceleration of like 8.44 blah blah blah. So that's just going to be 8.4. The two significant figures, which would actually with three significant figures would be appropriate here, because the data we've used is all this is 3 sig figs, 3, 3, so that 3 sig figs would be appropriate here. State and explain one characteristic of the aircraft that limits its maximum horizontal velocity. So this will be to do with air resistance, because at maximum velocity, forward force equals resistive force. So factors that affect air resistance would be the area presented to the air resistance, called the frontal area. The velocity is another thing that affects air resistance, but it's not really a characteristic of the aircraft. The fluid density or viscosity affects it, but again, that's not a property of the aircraft. So it's going to be essentially what's called the frontal area, or the cross-sectional area of the aircraft. I'm going to call it the frontal area in there, because that's what it's actually known as when you're doing this properly, of the aircraft. That's going to be the thing that affects it, because it's to do with the air resistance. So let's explain that, because a larger cross-sectional area leads to higher air resistance. And that reduces the speed at which forward thrust is equal to the air resistance, because that's when you reach maximum speed, when your forward force equals air resistance. So just those of you interested, there are a few factors that affect air resistance. So the force of air resistance, it's directly proportional to the frontal area, or the cross-section area. It's directly proportional to the velocity squared, normally, for an object traveling through air. And then there's a few other constants in there, and it's also proportional to like your fluid density, so air density, stuff like that. But that's a general rule of thumb to think about when you're dealing with questions. Okay, so that's that question right there. Let's carry on. So we're going to finish question 3. Okay, so on the axis below, sketch the velocity time graph for the horizontal motion of the aircraft as it accelerates from 0. So as I said before, the force of air resistance is proportional to velocity squared. So the force of air resistance gets bigger quadratically as velocity increases. So we'd expect the rate of increase of velocity to decrease over time. So it's going to look very much like your terminal velocity graph for an object under free fall. So initially we've got quite a steep gradient indicating that the velocity increases quickly, but then the rate of which velocity increases, or the acceleration, decreases over time to 0, and it ends up at constant horizontal velocity when the two forces are balanced. Okay, so state how a velocity time graph could be used to find the maximum acceleration. So acceleration is the gradient of this graph, so if we want to find maximum acceleration, we need to measure the steepest gradient, which would be at the start. So that's what we've got there. So we measure the steepest gradient would give us max acceleration. All right, so let's go on to question 4. Okay, so in this question we're looking at a stress versus strain graph for copper wire. I'm imagining we're going to look at some stuff like Young modulus and perhaps some work done to extend from this. So in terms of some features we can see here, so we've got this directly proportional section down here where we could determine Young modulus. We've got an ultimate tensile stress or breaking stress at this point where it fractures here, and we've clearly gone past the elastic limit somewhere up here to get plastic deformation. So that's the kind of the features I can see there. So let's see what it wants us to do. So the first thing it wants us to do is define tensile strain. So tensile strain is the extension divided by the original length. So let's put that down there. So tensile strain is the extension divided by the original length. There's an equation for that, but this is the actual definition of tensile strain. And the word tensile means you use extension, not change in length, because a tensile force acts to stretch an object, a compressive force acts to compress an object, surprisingly enough. So state the breaking stress of this copper wire. So breaking stress is the stress at which it fractures, which is up here. And then if we read across, that looks very much like 1.9 times 10 to the power of 8. So let's put that in there. 10 to the power of 8 pascals, or newtons per meter squared. Mark on figure 4 a point where you consider the plastic deformation may start. Label this point A. So let's eliminate some places. So it's not going to be in this sort of region here. This is just in your standard stretching a spring or an elastic material kind of thing. So it's going to be in this curved section up here. So I'm going to pick this location here because we're well past the straight line section, so we're going to be into the plastic deformation, and I did intend to mark that on the actual line. The accuracy of my stylus isn't great. So that's that point. Use the graph to calculate the Young modulus of copper. State an appropriate unit for your answer. So we're going to want to find the gradient of the straight line section. So let's pick somewhere that's quite nice to measure it from. So I'm going to go with this location right here. So let's draw on our gradient triangle. This, I'm afraid my stylus isn't particularly accurate, but this is, well, this isn't turning out too badly. Okay, so that's the triangle I'm going to be using. So change in y is going to be 84, 88, 92, 96. Change in y is 0.96 times 10 to the 8. Change in x, that looks like 0.8 times 10 to the minus 3. So let's put those values in. So Young modulus is to change in stress over change in strain for a straight line sections, that was 0.96 times 10 to the 8 divided by 0.8 times 10 to the minus 3. And when we put those values in. Let's calculate the answer. And we get an answer of 1.2 times 10 to the 11 pascals or newtons per meter squared. We could give either of those as the unit. Okay, so let's continue on. So the area under a line in the stress strain graph represents work done per unit volume so essentially the work done per meter cubed or whatever to stretch the wire. Use the graph to find the work done per unit volume in stretching the wire to a strain of 3.0 times 10 to the minus 3. So finding the area, we're going to use a counting squares method. So first of all, we need to work out what the area of one of the big squares is. So I'm just going to flip back and find that. Okay, so 1 square is 0.5 times 10 to the minus 3 times by 0.2 times 10 to the 8. So those powers of 10 give you 10 to the 5. Multiplying those two gives you 0.005. So that's going to leave you with 10,000 joules per meter cubed. That's one big square. So now what we need to do is count out the number of big squares. So I can't show you doing this because I can't split back and show you, unfortunately. But when I did this, I counted there to be about 39, I reckon, big squares there, maybe 38, but I'm going to go because I think it's like higher than that. So 39 squares. So that gives you 39 times 10,000, which gives you 390,000 or 3.9 times 10 to the 5 joules per meter cubed there. There'll be a range because the counting square method isn't too precise, but that's roughly what it is. And then calculate the work done to stretch a 0.015 kilogram sample to the strain that we were dealing with before, and we know the density. So we've currently got work done per unit volume. So what we need to do is work out what the volume is. And we're going to do that like this, so dividing the mass by the density, 1.5 divided by 8960, that gives us a value of 1.674 blah 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 times 10 to the minus 6 meters cubed. So then the work done is going to be our value from above, so 3.9 is 10 to the 5 times by that volume we've calculated. So let's do that. And we end up with a value of 0.65 joules there for the whole sample. Okay, so then a certain material has a Young modulus greater than copper and undergoes brittle fracture at stress of 176. Draw a line showing the possible variation. So if it's brittle, you're not going to have a plastic region, so you're just going to see a straight line graph. So I can't show you this, so I'll just write what I would do. So it's straight line graph, and it's going to fracture at a stress of 176 megapascals. And in terms of how it would compare to the previous one, if it's Young modulus gradient, so it's going to have a steeper gradient than the original graph. So as long as your line shows those two things, those are going to pick up the 2 marks for this part of question 4. All right, so let's move on to the next question. All right, so now we're going to look at a diffraction grating, so some interference, and we're going to do it with white light. So complete the diagram to show the light beams transmitted by the grating, showing the 0 order and the 1st order beams. So what you get with this is you get a, if we draw across, we're going to get a central fringe there, and then we're going to get in the outer fringes, what we're going to get is a splitting of the wavelengths. So let's try and show that. And then this is your n equals 1 and your n equals 1 there. So let's label what they would look like. So the central fringe, as I said, is going to be white. They should be roughly equally spaced on here. And then from here, what we're trying to show is we're going to go violet on the inside, red on the outside, and you'd have a full spectrum in between, going through your like blues, greens, yellows, oranges, those kind of things. So that's what the kind of general idea would be like using white light. So light from a star is passed through the grating. Explain how the appearance of the first order beam can be used to deduce one piece of information about the gases that make up the outer layers of the star. So when we use a diffraction grating, it would split up the light into its different wavelengths, so you get all the colours of the spectrum in theory if the star is emitting white light, but there'll be some missing wavelengths where the outer atmosphere of the star has absorbed the radiation. These are called Fraunhofer lines, and that's where you actually get the information from. So let's put that down. All right, so that's what we've got there, and it's these missing wavelengths that tell us essentially the energy of the photons that have been absorbed by the atmosphere of the star, and then we know which photon energies correspond to which elements, so that's what tells us what they are made of. So in an experiment, a laser is used with a diffraction grating of known lines per millimeter to measure the wavelength. So I'm sensing we're going to be designing an experiment in a second. So it wants us a diagram of the apparatus. So because it's a laser, we don't need a single slit here. So we've got our laser. Let's say it's shooting at red light, and then we're going to have a diffraction grating. We're going to have a screen, and then what we would see on it is essentially it splitting up into the different orders like that. So let's label our pieces. So that's a diffraction grating. If this pen wants to write. This one over here is a screen, and then this over here is your laser box that we're going to be using, and we would want to make sure that the laser is perpendicular to the slits, and the slits are parallel with the diffraction grating is parallel with your screen. So that's the stuff that you need. Oh, what a surprise. Describe the necessary procedure to obtain an accurate and reliable value for wavelength of the laser light. You should include details of all measurements and necessary calculations. Generally, so things I'm thinking, so accuracy is about eliminating errors, so we're going to be doing in a darkened room, so it's the fringes are already clear, so you can measure from center to center on them. Reliable, that's telling us we're going to be taking repeat values of measurements and then finding out averages, stuff like that. So measurements, we're going to be measuring fringe spacings and the slit screen distance, so we can work out what the diffraction angles are in each case, and then we're going to use the diffraction grating equation on our graph to work out wavelength. So that's the general idea. So let's start putting that into reality. Okay, so that's what we've got here. We've got the first stages of setting this up. So we're going to have the laser, making sure the laser is perpendicular or normal to the diffraction grating, and making sure it's pointed away so it's not a risk to other people. And then we're going to place the screen a fixed distance of 5 meters from the diffraction grating, and we're not going to measure that to make sure we've got that value, because we're going to need that later on. So then what we're going to do is we're going to measure the spacings between each of the orders. So we're going to measure the distance between the 2 first orders, the 2 second orders, the 2 third, and that's going to allow us to work out what the spacing is in each case, and from that we'll work out the diffraction angle. Okay, so let's get that down. Okay, so what we're going to do is measure the distance between n equals 0 and n equals 1, and we're going to do that by actually measuring 1 to 1 and dividing it by 2. And then we're going to determine the angle to the first order using a tan rule, would allow us to work out what the angle is. So then we're going to need to find out the distance between n equals 0 and the other orders. So we're going to repeat this process for the other orders. Okay, so that's what we've got here. So we're going to repeat that whole process for the other orders. So for n equals 2, 3, up to 7 if there are that many orders, and then do the whole investigation again. So we've got average diffraction angles for each order. So then if we have a look at our diffraction grating equation, so the diffraction grating equation is this one. So we know what d is, we've changed n, and we've measured theta, and therefore we can measure sine theta. So what we need to do is first get this into y equals mx plus c form. So sine theta is lambda over d, that's the gradient, times by the order. So what we're going to do is we're going to plot a graph of sine theta against n, and multiply the gradient by the slit separation to give the wavelength. So that's what we've got there. Let's talk about what we were supposed to have got in this answer. So have we got a procedure to obtain accurate? Well, we've got average values of the diffraction angle. That's a strategy to improve accuracy. I can think of one more I need to write about in a second. Reliability, yes, we've done repeat readings. We've got the measurements we're going to take. We've got calculations we're going to do. So let's just put in one more strategy to improve accuracy. So this is what I mentioned earlier about doing it in a darkened room to make measuring between centers of the fringes more straightforward. So carry out the proceed in a dark room to improve the accuracy of measurements of fringe spacings, because if you do it in a darkened room, it's going to be the fringes are going to be much clearer without the interference of outside light, so making those measurements was going to be more accurate. All right, so that finishes that question. Let's move on to the next one, questions. All right, so we've got a prism, so we're going to be dealing with some refraction. So light is directed into the prism at an angle of 56, so that's our angle of incidence, and the angle of refraction we can see is 30 degrees. Calculate the refractive index of glass. We're going to be assuming it's going from air, which has a refractive index of 1. So applying Snell's law, at least if you agree Snell came up with it. I would dispute that, but let's not worry about that for now. And then is refraction. So we can get rid of n1 because it's 1. We know sine theta I and theta r, so we can get n2. So n2 is going to be sine of theta 1, or the angle of incidence, which is 56, divided by sine 30, and we get a value of 1.6858, or 1.7 sig figs. Then it wants us to calculate the critical angle for the glass air boundary. So the critical angle is when it's going from glass into air, because that's when it's decreasing. So it's going from high to low. So in that case, N1 would be 1.658, blah, blah, blah. N2 would be 1. And sine theta r is going to be 90. So essentially what we're going to have is, in this case, N1 sine, the critical angle is going to go to air, so that's going to be 1. Sine of 90 is 1. So actually, the critical angle is going to be the inverse sine of 1 over 1.658. That way around, which if we calculate that to appropriate numbers and significant figures, is going to be 37 degrees there. So if you've done this calculation and you ended up with a maths error, it means you've got your N1 and N2 the wrong way around. Remember, critical angles only occur when you go from high to low, so it's going from glass to air. So that's the common mistake people would make. On figure 6, continue the path of the ray of light until it emerges from the prism. So the first thing it's going to do is go to the glass air boundary. Okay, so if we look at this, it rounds the boundary at an angle of incidence of 60 degrees. That's greater than 37, so it's going to be reflected off that boundary there. And that's going to happen until it reaches this other boundary here. So let's draw a normal here, and then we're going to need to work out the angles involved. So we know this angle in here is 60 degrees. Let's construct a right angle triangle here. So this one up here must be 30 degrees. It makes up a full right angle. That's 90. That whole thing, this whole angle in here would have to be 120, because that one plus that one plus that one have to be 180, which means this angle in here is going to be 30 degrees. So that's going to be your angle of incidence, which is less than the critical angle. So we're going to get refraction occurring. It's going from high to low, where it's going to bend away from the normal here, like that. So it's going to bend away from your normal. So angle of refraction is bigger than your angle of incidence there. So it's going to look something a bit like that. Okay, so that completes this question here. Let's move on to the last question. Okay, so we've got a progressive wave on a rope, and we've got a knot in the rope, presumably so we can track its location. So the first thing I want us to do is define what an amplitude of a wave is, and it's the maximum displacement of a particle of the medium from its equilibrium position. So let's get that down. So that's how amplitude is measured. So the two parts there, it's maximum displacement and it's from the equilibrium position is the second mark there. The wave travels to the right. Describe how the vertical displacement of the knot varies over one full cycle. So the way I always do this is think about, where would the wave be in like a few units of time away. So a little bit later, the wave, this is so poorly drawn and rough, but it helps you get the idea. So this is where the wave is going to be in a few moments time. So we can see the knot has moved down here. So the first thing that's going to happen is it's going to go downwards to maximum position. It's going to go back to the equilibrium position, then it's going to go upwards and then back to the equilibrium position. That's the order it's going to go in. The way I would do this is, if you looked, because the wave is going across to the right, what's coming next will be to the left. So you can see that what's coming through is a minimum is coming that way. So that tells you what's going to happen first. So we're going to do over the whole cycle. So it's going to go downwards for maximum first. Alrighty, and that's what would happen over a full cycle there. So then a continuous wave of the same amplitude and frequency moves along the rope from the right and passes through the first wave. The knot becomes motionless. Explain that would happen. Well, we've got two waves of the same frequency and amplitude. So what's going to happen is we're going to form a stationary wave. So the two waves will superpose on one another. And the reason the knot doesn't move is it's in a location of destructive interference, so then you formed a node. So let's get that. All right, and that's what we have got there. So that's why the knot doesn't move. Okay, so that completes this question paper. If you've spotted any errors or things that are not clear as you've gone through, please do let me know and comment on this video so I can see it. Please do make sure you check out my other playlists on Unit 1, 4 and 5 and the other videos in this Unit 2 series to help you with your exam preparation. But most of all, thank you for taking the time to watch this video. I hope you found it useful.